About is confidence intervals for a population proportion. All right, so this will be your first of many inferential procedures that you're going to have to know for the course. All right, let's do that. All right, so go ahead and write down this formula for me, please. Go ahead and write down this formula for me. We kind of talked about this formula yesterday and how it was kind of derived. As you're writing down this formula, what does p hat represent? Sample proportion. Plus or minus. Does anyone remember what z star represents? Critical value. Okay. So we talked about finding those z stars. Do you remember how many z stars we are going to be required to memorize? 3. Anybody remember those? For 98% confidence, 95% confidence, and 99% confidence, right? What's the one for 90? 1.645. What about 95? And then the last one? Okay, and those are, remember, z stars are upper z scores, okay? Yesterday we talked about describing how we actually got those. We did a normal distribution, very similar to this, where we were talking about a confidence level is between 2 z stars. So we had a negative z star and a positive z star. And we were interested in finding this interval with like so much confidence. So for instance, like 95. That z star is the upper z score for that. So the z star is the upper z score for that. We talked about how to derive each of those. What do we call the square root of p hat q hat over n? The square root of p hat q hat over n. What do we call that? The standard deviation of our statistic, right? And what statistic are we talking about? Which one of this is a statistic up here? P hat, right? So very similar. So again, remember we called this p hat something special yesterday. What do we call p hat? As a name. A point estimate is the first line of like estimation, right? So if you don't know your population proportion, the first thing you do is you take a sample and calculate a sample proportion. Let's call that a point estimate. That's your first go-to. However, Chandler reminded us yesterday that we have sampling variability. So we know that each sample is going to vary, correct? So we created this thing over here, which is z star times the square root of p hat q hat over n. What do we call that from yesterday? It's like combining these two. It's 3 words. It's the margin of error, right? So we are talking about each of these pieces here, but together all of that is going to be your margin of error. Okay, so all of that's going to be your margin of error. And again, why are we using p hat instead of p? Because we don't know p. Remember, what is a general confidence interval idea? Like, what are we doing? We're estimating p because we don't know its true value. It's unknown. So the next best thing that we use is p hat. All right. So here we're trying to figure out what, with confidence, where do we think p lies? All right. All right. Introduction into panic. Now, this is going to be a little acronym that you're going to use to remember the components of completing a confidence interval. Generally, when you're asked to do a free response question, you're asked to construct and interpret a confidence interval in context. All right. Whenever you see the words construct and interpret a confidence interval, you're going to remember to panic. Not actually panic. I know some of you guys are like, oh, panic, that's what I usually do in stats, right? Yeah. Not the actual feeling of panic. You're going to remember the acronym panic, okay? First thing means that you're going to state the parameter. So P represents the parameter. What are you attempting to estimate? And we're going to go through an example of this today. So what are you attempting to estimate there? The second is you have to check all assumptions, okay? Actually, I lied here. There are not going to be 3. There are going to be just 2. They're going to be just 2. So amend that. There's only going to be 2 there. You're going to then name the interval. So you're going to call it what it is. That's when you're going to look at the list on the board over here, the whiteboard. You guys see the inferential procedures now list. that's when you name it. You're going to learn different ones, different days. So this week, you're going to learn 2 inferential procedures. The first being a 1 proportion Z interval, the second being a 1 sample T interval. And we'll talk about the difference between those this week. Then you must have your interval. You got to show all your work for your interval. And I'm going to show you exactly what that looks like. Again, if I show you what it looks like, do I want you to deviate from that? No, I think you guys have learned the lesson about deviating from that, correct? Yeah. Okay. And then finally, you're going to write your conclusion in context, all right? And we're going to talk about the conclusion that you must memorize, okay? Because it's going to be the most accurate representation, or the most accurate interpretation, as I should say, of a confidence interval in context. All right, so we're going to go through all of that in our notes. All right, let's go to assumptions for estimating P. We must check 2 conditions. All right, the first one is that you have a simple random sample or some sort of random assignment that needs to be happening. So this is going to be for number 1 in those notes. So you have to have your data come from either a random sample, could be a random sample of just citizens, a simple random sample, a stratified random sample. What's the key word? Random. It must be some sort of randomization. However, sometimes you have an experiment. Experiments, my friends, are not samples. So if it says that they were randomly assigned and you quote unquote use SRS, that is not going to give you credit. So you really need to read the context of your scenario to understand if a random sample was taken versus a random assignment of treatments. But some sort of randomization factor needs to be within that, okay? The next thing is that you have to check for the sampling distribution normality, okay? So you must check to see if you can use the normal distribution. Remember, we're talking about the sampling distribution as normal or approximately normal. Again, that can be given to you. How could it be given to you that it was normal? Because you know your population distribution is normal. They'll say like your population is normally distributed, right? So that's how it could be quote unquote given to you, right? Remember, it can also be this. Now, you guys often can use the condition checks between the 1 proportion Z interval and the 1 proportion, or excuse me, the 1 sample T interval. Here, this is when we're going to check for NP hat and NQ hat greater than or equal to 10. Remember that this was back from 7.2 for sample proportions. What does it mean to have greater than 10 for each of those? Does anyone remember what we talked about? Like NP, NQ, what were those? Very good. It's the number of successes and failures. So you must have at least 10 successes and 10 failures to suppose or assume that your sampling distribution will be approximately normal. Oh, sorry. Are you guys good there with the conditions? These are the 2 things you must check. So do you guys remember from A for panic, the A part where it says assumptions? That's what you need to check. You have to check both of these. All right. And we're going to lay out a full confidence interval constructing and interpreting by hand. So you're going to see all those key pieces today. Okay. Do you guys have any questions about the assumptions before we move on? These are major 2. Yes, no, maybe so. All right, moving on. All right, your conclusion. This is how I would like you to interpret every single confidence interval that you have to I guess, count. Right? You're going to say that we are, or you can say I am, but generally it's we are blank % confident. We are this confident that the interval from the low bound to the upper bound captures the true proportion / mean of your context. And we will kind of go over that. So this is when you're going to use your confidence level here. We are confidence level confident. So if it's 90%, you put 90%. If it's 95, you put 95. So this is what you're Yes, we were kind of informally doing this, but this is the exact way that it needs to be done. Okay, because this is what it truly means to have a confidence interval. Okay, so what is a confidence interval? It's when you are this confident that the interval from your lower bound to your upper bound captures the true mean or the true proportion or whatever it is you're estimating in context. Again, we have no idea if the true mean or the true proportion fell within that interval. But we're 90-something% confident, 90, 95, 99, 98, that it does. But we don't know if it did. We're just that confident based on what our calculations are. Okay? So you guys have that written down. You need to have that written down. Do me a big favor. Star this. Please do not deviate from your interpretations of the confidence interval. Today is a really big day, guys. Today is a really big day because we're going to be doing multiple confidence intervals. We're going to be talking about 1 sample confidence intervals and 2 sample confidence intervals. So this is not the last time you're going to see confidence intervals. This is just the beginning of inference. All right? Today you're putting your toe in the water. By the end, you're going to be knee-deep, underwater in inference. Okay, hopefully not drowning. Hopefully treading water. Scuba diving. There you go. That's a good thing. Okay, so let's do an example of what this looks like, shall we? So what does this look like start to finish in terms of us constructing and interpreting the confidence interval? So you're going to be given some scenario, like example 1. In May 2011 Gallup poll, it found that 38% of a random sample of 1,012 adults said that they believe in ghosts. Find a 95% confidence interval for the true proportion of adults who believe in ghosts. All right? Does that make sense? You understand the scenario? What does this 38% represent? Is that P? No, it's not P because we don't know what that is. What is this? That's P hat. You guys with me on P hat? Okay, cool. So you guys need to be able to understand, like when you see a proportion, is that a P hat or is that a P? That's very important because sometimes I don't think you guys read very carefully. So that's P hat. This is our N, right? So we have 1,012 adults. And just kind of highlighting some other things. Anybody else recognize anything that's kind of maybe of importance that or significance? So this is going to be our 95% confidence interval. So this is going to be what we're going to construct, right? Maybe this idea that it came from a random sample. Does that mean at least one of those conditions that we kind of talked about earlier maybe okay? Yeah, I think that's good. So just piecing out like, okay, looks like some good stuff's going on here. All right, let's formalize it. You guys ready? All right, your first of many confidence intervals, my friends. All right, first thing you want to do is P, right? State the parameters. So we want to estimate P. That is what we're doing. We're stating what the parameter is. We want to estimate what P is. And P here is going to be equal to the true proportion of adults who believe in ghosts with 95%. That's what we're doing. Okay? So when we're stating the parameter, we're defining what P is. P here is the true proportion of adults who believe in ghosts. That 38% that we found is not P. That's not the true proportion. That is the sample proportion, right? Based off the 1,012 adults. We're looking to figure out what the true one is for all U.S. adults. We're trying to infer about what the population believes based off our sample. Does that make sense? So that's when we're stating this parameter. Okay, so you need to write all of them. So please write every single word. You must do it like this. So if you're not writing, you need to be writing. Okay. How many assumptions do we have again that we need to check? 2. What's the first? Do we have randomization? Is it an SRS, a random sample, random assignment? From the comments, like from the, or not comments, I guess from the context of the problem. we have a random sample of 1,012 adults, correct? So we need to state that. So just write assumptions and then say, number one, we have a random sample of 1,012 adults. So that means that we're checking to see if randomization was used within the construction of this concept. And it was. So we use randomization from a random sample. What's the second thing we have to check? Approximately normal. How do we go about doing it? How do we check for normality? NP hat and NQ hat. Is that very similar to 7.2 when we checked NP and NQ? What's the only difference? It's P hat instead of, and why is it P hat instead of P? Because we don't know P. So what do we use? That's all we got, right? Okay, so we're going to do our normality check. So here, if you want to go ahead and write this down, I'll save you some of the work. You need to take 1,012 and times that by 0.38. Take 1,012 times that by 0.62. Preferably, I would like you guys to write NP hat is greater than or equal to 10, and NQ hat is greater than or equal to 10. Then plug it in. But I think I'll live if you do that. All right. Do you think it's true that we have at least 10 successes and 10 failures? So what can we say? It is very vague. Let's amend it. The sampling distribution of what? The sampling distribution of P hat is approximately normal, right? Or that there are at least 10 successes and failures, so the sampling distribution is approximately normal. Say both. Because when you're checking for 10 successes and 10 failures, you're really checking to see if the sampling distribution is approximately normal. We did put here that we're checking for normality, just really making sure that you know what you guys are checking for. What's the N part of panic? Name it. What is the interval, I guess, procedure that you're going to be learning today? It's a one proportion, and the reason it's one proportion is because it comes from one sample. So when you write one proportion Z interval, you're saying that you have one sample with one proportion, and you're constructing a Z interval using the normal distribution. All right? So that's basically what you're saying in words. Okay? Say one proportion Z interval is what you're going to be performing. So you got to name it. All right, we need to now start thinking about the interval itself, correct? So how are we going to construct this interval? Do you guys remember the first thing that you wrote down today? You wrote down the formula, correct? Okay. So the first thing you wrote down is the formula, which is P hat plus or minus Z star times square root of P hat Q hat over N, correct? It's the first thing you're going to write down, so go ahead and write it down. So interval for I. Going to be P hat plus or minus Z star times square root of P hat Q hat over N. All right, what was P hat? 0.38. So you have 0.38 plus or minus. What's the Z star for our confidence level? Remember, you said what confidence are we using?
95.
And what's the upper Z score for 95? 1.96. Times square root of P hat Q hat. P hat you told me was 0.38. Q hat is going to be 0.62. And you're going to divide that by our sample size of what? 12. calculate. First thing I like to do is I like to calculate this standard deviation statistic. And I got 0.0153. Can someone confirm that I did that correctly? So then, what am I going to times here? 1.96, which is going to be plus or minus 0.0299. 0.38. I'm just doing the 4 decimal places. And then over here, I'm going to have the negative version, and over here, I'm going to have the positive version, right? So I'm going to do 0.38 minus 0.0299, and that gives me the interval of 0.3501 on the low bound. 0.38 plus 0.0299 gives you a high bound of 0.4099. Generally, when you make an interval, you kind of use parentheses around it. So it's from this to this. Okay. So do you guys see the interval that you found? Very similar to what we did yesterday with the Hershey-Kiss activity. You guys have questions about how we compute this interval? Nope. Okay. So I'm going to bring back up the work from the PowerPoint. Skip ahead so we can interpret this. Okay. So do you guys agree this is the work that we have? Okay. All right. So what are we going to do now? We're going to interpret this. So let's go back to the interpretation page. All right. What are we doing? We are estimating with confidence, correct? So how confident are we? We are 95% confident that what? That the interval from 0.3501 to 0.4099 does what? Captures the true proportion of what? Of U.S. adults who believe in ghosts. All right? So you can go ahead and copy that down. So we kind of just piece that together. So now here it is. So you can write it down. We are 95% confident that the interval from 0.3501 to 0.4099 captures the true proportion of adults. You can say of U.S. adults. I think it was U.S. adults, correct? That's fine, either or. Who believe in ghosts? So we're about 95% confident that that P that we don't know is between basically 35% and 41%. You guys think that's true? Well, maybe. I might start now that I've been thinking about this problem. How was your first one proportion Z interval? Not that bad? Okay. You guys have questions about anything that we did there?
Panic every time.
You have to do panic every single time that you see the words construct and interpret a blank percent confidence interval. Okay? And panic is a short one. Oh, you haven't seen long yet, my friend. You have not seen long yet. These are the baby ones. Okay. All right. You guys see example 2 on your notes? What I'm going to do is I'm going to give you guys about 10 or so minutes. And I want you to do as much as you can of panic using our first example as kind of like a template to see if you can answer the question for example 2. All right? Or kind of, I guess, find what they're asking for. In October 2010, the Gallup poll asked 510 randomly sampled adults the question, generally speaking, do you believe the death penalty is applied fairly or unfairly in this country today? Of these, 60% answered fairly, 35% said unfairly, and 4% said they did not know. Construct and interpret a 90% confidence interval for the true proportion of all U.S. adults who think that the death penalty is applied fairly. So when we're saying applied fairly, what proportion are we looking at here from our data? Which one will be our p-hat? So we're looking at the 60%, correct? Okay, so just make sure you pick out the correct proportion. All right, I'm going to give you guys 10 minutes to work. So I'm going to pause this. You guys do it too. All right, time to go over said example 2. All right, so let's see what you guys did. Did you guys say that we want to... I actually did put a 10-minute timer on. All right, we want to estimate P, which is equal to the true proportion of U.S. adults who think that the death penalty is applied fairly. Okay. I do want you to make a note. Can you read your true proportion statement that you say there? It cannot be in past tense. I really want you to look at that. Your true proportion, when you're defining your parameter, cannot be in past tense. It has to be in present tense. I know this seems weird that the English matters. Okay. Anyone want to ask the question?
Why?
Why? Good. If you refer to it in past tense, it's assumed that you're talking about something that's already happened. And what has already happened? The random sample. So when you talk about your parameter in past tense, it's basically you referring to the sample. It's talking about sample data. Is a proportion like this proportion, this P, is this a sample? Is this from a sample? Is it a statistic? Answer is no. What is it? What is P? It's a parameter. Parameters describe all at any point in time. So you need to say who think or who will think, not who thought. Do you guys see who thought? So that means they've already answered the question. It means they could have already done it. Does that make sense? I know it's really nitpicky, but it's something we're going to continue to have a discussion on because I literally have to take off points on the AP reading when we looked at past tense versions of defining parameters. Okay? So I'm trying to help you help yourselves. You guys go with that? All right, you check your assumptions here. You have a random sample of 510 adults. You say random sample of 510 adults.
Yes.
Excellent. Did you check for normality?
Yes.
What did you say after you checked for normality where you had 306 greater than or equal to 10 and 204 greater than or equal to 10? There are at least 10 successes, 10 failures. So?
The sampling distribution is approximate.
Very good. Sample distribution of p hat. Okay. You can get away with just this, but I want you guys to do it for now. Because I really need you to understand what you're checking.
But we don't just say sampling distribution, we have to say
The sampling distribution of p hat. What sampling? Because it goes like you would say it's what's it? The p hat. If you kind of define what p hat is, if you go on your paper and say p hat equals this, then you can say the p hat.
Oh, okay.
It should be of p hat because you got to remember that the sampling distribution is not just a single p hat value. It's a representation of all p hat values over time, over many samples, over all possible simple random samples. I would say the sampling distribution of p hat. That's the best way, because anything else may refer to something different. I know it's really nitpicky, but it's really important that you understand that you're talking about the sampling distribution, not the actual. Because do we actually know what the proportion or the population of this looks like?
No.
Have no idea. But we can comment on the sampling distribution, right? It's approximately. Did you name it? Excellent. Formula? Formula? 0.6 plus or minus 1.645 times square root 0.6.4 over 510. Intervals? Got it. 0.5643 to? My heart is Conclusion?
We are 90% confident.
Because the interval of 6.5, 6, 4, 3, 2, 6, 3, 5, 7, 2.
They have no unison. They're just all randomly saying words at the same time.
We are 90% confident that the interval of 1.5, 6, 4, 3 to 0.6357 captures the true proportion of the multi-difference
It was pretty. It was rough start, really good middle. Kind of fell apart in the end, but I think it was there. I applaud your effort.
Thank you.
That was good. That was good. That was fun. It's good to do that. All right, you guys good with this? Okay. So how is doing this?
Not bad.
It's not bad. It's a little long, but overall, I think it's. Do you know what you're doing though? I think it's important to understand what a panic in this case is, because I don't want you just to go through the motions of doing all this and not really understand what it is you're actually doing. Someone raise their hand and tell me, what exactly are you doing? Amy.
You're finding, or you're saying that the true proportion of I don't remember what the true proportion of all US adults who think that probably is a 5 fairly is between the two values given, and we're 90% confident that it is.
Okay. Do you know if it is in there? No. You'll never know. But we're about 90% confident it's between these two. That's all we can say.
So they're always gonna give us confident.
Confidence level? Yeah. They generally, because they have to tell you how to do it, right? Or if you're making your own, you can be as confident as you want. Okay? Because the more confident you are, the better estimate you're going to get. Because remember, your range is going to be wider. So a 90% confidence is smaller in interval than a 99. The more confident you are, the more likely it's going to capture that true mean, or true portion.
It's always gonna be one.
Generally, those are the big three. The 90, 95, 99. Those are the big three. Yep. Sometimes you can deviate. Like on your homework, you have a 98. I'm just trying to see if you were listening yesterday how you can derive Z-star. That's more of an assessment there.
Yeah, for inverse norm, that's what I was like.
Okay, so if you want to find the Z-star for 98, remember, it's on a normal distribution, right? Confidence interval goes from a low bound to a high bound, right? So we're going from low bound to high bound. And how much of that area is going to be covered if you're talking about a 98% confidence interval? 98% of this area is here, right? So then, what area is left over underneath the normal curve? 2%. So each tail gets 1%, right? And again, what's our Z-star? Again, Z-star is the upper Z-score, right? This is that Z-star value. So we wanted to find, what area is below that? And remember, we used inverse norm to do that. Because we want to find area below a specific point on a normal curve, you use inverse norm to do so, right? So remember, it's like a percentile kind of thing. What percent am I going to put in there for inverse norm? 0.99, 0, and 1. And that is going to give you this thing right here is equal to your Z-star value. So you can always derive it for any confidence level, but those are the big three, which is why you have to memorize them. Does that make sense? Yeah. Okay, cool. You're going to get better at this whole thing. Do you know what I just drew here? Now I'm erasing. When you're talking about one sample T intervals, you have to do it all the time. You have to go find it. And we'll talk about doing that. All right. Yeah, T interval. I know. You're like, T? Where the heck T come from? We were just talking about Z. Why T? Well, guess what? Stay tuned and I'll teach you about it. All right, let's talk about determining sample size. So here we have some little scenario, right? Another Gallup poll is taken in order to measure the proportion of U.S. adults who approve of attempts to clone humans. These are things that happen, right? I mean, talking about cloning humans now, right? We're going to talk about this. What sample size is necessary to be within 0.04 or plus or minus 0.04, of the true proportion of U.S. adults who approve of attempts to clone humans with a 95% confidence interval. All right, so here they're trying to basically say, all right, you're going to construct a 95% confidence interval, right? And you're going to have some p hat that you're going to use to do that. But you want your margin of error to be bounded. Like, you don't want it to go over. Two things control how wide your confidence interval is. First thing is how confident you are. Confidence level. The more confident you are, the wider the interval. The other thing that controls how wide the interval is your margin of error, your sample size, right? Because we know with higher samples, we have lower variability. So if you want a specific margin of error, you're going to need a certain sample size to achieve that. And that's what you're doing in this problem. You're trying to achieve a specific sample size to limit your margin of error because you want to be so confident. So basically, it's like you're defining, like, for lack of a better word, the parameters. Like, you're defining what you want from your confidence interval, and then you're trying to find what would help you achieve those goals. Yes? Okay, cool. All right, so to do this, you have a nice little formula. And this formula is no different from when you're looking at your confidence interval itself. Do you guys remember what we talked about the margin of error being today? Margin of error is equal to the z star times your square root of p hat q hat over n, correct? Go ahead and jot that down. So you need to understand what your margin of error is going to be equal to. It is everything that's to the right of the plus or minus. A couple big disclaimers here. If they don't give you p hat, you're going to have to choose a p hat. Notice in that sample, they didn't tell you what p hat was. Nowhere in there did they say the sample proportion was blank, right? So that's a problem. And we're going to have that discussion right after this to figure out what p hat to use. Sometimes they'll suppose a p hat, or they'll give it to you, but then there's a general formula that you'll use, like a generic one, if you're not good. Okay? So margin of error is z star times square root p hat q hat over n. This is no different from the confidence interval formula itself. I think I spot into that. It's no different. It's just after the plus or minus. You don't put plus or minus with this. So, and when you do this, you're always going to round up to the nearest person, because higher sample sizes never happen. Okay? So if you get like an answer of like 27.2 people, n equals 27.2, you're not going to do 0.2. You're going to just round up to the next whole person. And 27.2 doesn't round down. You always literally round up when you're talking about sample size. So if it's like 27.001, guess what you're going to do? 28. You're always going to round up, regardless of the decimal with sample size. Always round up. Okay. You guys ready to talk about how we're going to determine what p hat we're going to use? That's pretty important. So what p hat do you use when trying to find the sample size for a given margin of error? Okay. So if we were to choose p hat to be like 0.10, right? Q hat would be 0.9, which would give you 0.09, right? When you multiply them. And what I'm referring to is, I'm talking about inside this square root, p hat, q hat over n. I'm talking about there, okay? We're talking about these two values, and when you multiply them, you're going to get 0.09 over n if you use p hat to be 0.1 and q hat to be 0.9. You with me? Okay. If you choose 0.2 and 0.8, what do you get here? 0.16. 0.3, 0.7, you get 0.4 and 0.6, you get, and then 0.5 and 0.5, you get. So what you're going to do here is, I want you to notice which value is going to be the largest. Which one, when you take the product of p hat, q hat, is the biggest? 0.5. So what I want you to do is make sure you write down this value. We're going to talk about why in just a second, but you're going to use 0.5 for p hat if a p hat is not given to you. The reason you're going to use 0.5 for p hat if one is not given to you is because it's going to give you the most error. I hope you understand it's going to give you the most error. because that number on the numerator is going to be higher than any other p hat value. You guys see how we compared them to 0.1, 0.2, 0.3 for p hat? When you took the product of p hat, q hat, it was smaller for each of those values until you got to 0.5. And this is going to allow you for the largest standard deviation. So worst comes to worst, we call 0.5 using that the worst case scenario. That is literally the worst case scenario. So if you don't have another p hat, you use 0.5 because it's going to give you the most error. So basically, if your p hat turns out to be, I don't know, 0.3, that's a product of 0.21, which is smaller than what? Which means that if you have that sample size of whatever it is after you calculate it, you're still going to be within your margin of error. Does that make sense what I'm talking about? Yes. Because that number is going to be bigger. Okay, so like remember we're talking about 0.25 over n, right? So if this number is bigger, when you divide n into it, it's still going to be a bigger number. So for instance, if you want to choose like n to be, I don't know, 0.25 over, like I guess 4, type that in your calculator. Like what's 0.25 divided by 4? Take the square root. That's 0.25. Can someone confirm that's still 0.25?
Yeah.
Okay. So I have a question. If you type in 0.21 divided by 4. 0.22 what? 91. Which one has lower standard deviation? So this has more standard deviation than the 0.21, right? So this has more error accounted for. So that means your sample size when you compute it is going to meet that margin of error requirement of, like in the cloning humans one that we're about to do in just a second, right? Of 0.04. So since this has smaller error, with this sample size that you obtained over there, this is still going to have like enough sample size to make that margin of error met, like that 0.04 restriction, if that makes sense. Okay. So basically, by using 0.05, or not 0.5, you're having the most error. That was the most error. Let's do an example. You guys ready to see the example? It's the same example from earlier. It's the cloning example, right? So what's the first thing that we're going to do here if we're trying to talk about the margin of error and we're trying to determine sample size? Well, we know that the margin of error is going to be equal to the critical value, z star, times the standard deviation of the statistic, p hat, q hat, over n. All right. All right, let's identify what you know and what you don't. We don't know p hat, right? That's unknown. So what are you going to use as proxy? 0.5, because you don't know it, so you're going to use 0.5. Because again, 0.5 is going to allow for the most error. So if our p hat happens to be above or below that, fantastic. We know the error is going to be less. But this is going to be the most error. So q hat is going to be 0.5. What else do you know? So I've got the numerator taken care of. Remember, you're trying to figure out what sample size, right? So n is going to be what our goal is to find. You guys agree that's our goal to find there? So we're trying to find n. So we don't know n, we know p hat, q hat. Do we know z star and the margin of error? Because we need all the other variables to have numbers. And why are we using 1.96 as z star? So this 95% confidence gave that away, right? So if you're using 95% confidence, this upper z-score, where that critical value is going to be 1.96. So what's the margin of error going to be? What? 0.04. You don't need to include the plus or minus with it. All right, so it's just 0.04. All right, substitute. So 0.04 goes in there for margin of error equals 1.96 times square root of 0.5 times 0.5 over n. So you just substitute it in. So margin of error is 0.04 equaling z star, which is a critical value of 1.96, times square root of 0.5 times 0.5 divided by square root. or divide by n, not square root. Square root of 0.5 times 0.5 over n. All right. Can I go ahead and just write this again as, instead of doing 0.5 and 0.5, are you guys okay with just me writing 0.25? Is that cool? All right, we're going to solve this a little weird. All right, but it's not hard. I want you to think about this stuff. I want to solve for this n value, correct? You can see that n value there? I got to get that off the denominator, and I have to get it out of the square root, correct? So first thing is I'm going to take care of the square root thing. I'm going to go ahead and square everything. You guys see how I can square everything? You square everything, the square root will go away. So the reason I'm squaring is to get rid of that square root over there. So over here I have a fraction of 0.25 over n times 1.96 squared times 0.04 squared. You see how I just squared everything? Now I'm going to rewrite this a little bit. Do you guys agree that this is 1.96 squared times 0.25, then all divided by n? Can I do that? Because when you're multiplying two things, like you're multiplying 3 times, like I guess a half, right? What would that give you? You guys agree? The only thing that I did here was I wrote as 3 times 1 over 2. And then the same thing as 3 halves. So now the only thing that you need to do is move n off the denominator. How can I move n off the denominator? Multiply both sides by n. So I got n times 0.04 squared equals 1.96 squared times 0.25. So then what can I do with this 0.04? Divided. So what is almost happening here with the n and the 0.04? They're like switching. You guys see how they're like switching? So now n is where I want it to be, alone on one side. And I got 1.96 squared times 0.25, all divided by 0.04 squared. You guys agree with that? Mm-hmm. So now, notice I didn't use a calculator until this moment. Guess I have not used a calculator yet. Yeah. Once you get n by itself, then put this in the calculator. So go ahead and put this in the calculator. Take a minute and tell me what it is. So you try to see if you can type that in the calculator. So you need to do 1.96 squared times 0.25 divided by 0.04 squared. So you said 601 point what?
It's 625 around.
So 601. Oh, it's 600.25. Okay, so it's 600.25, which we're going to round what?
Yeah.
Remember, more times that's never happened, right? So here, what does this basically tell us? If we sample 601 people and construct a 95% confidence interval with a p-hat of 0.5, we're going to get a margin of error to be within plus or minus 0.04. So again, this is you controlling how wide your interval is, okay? And how much error you have within your estimation of what. Again, what are we attempting to do when we construct a confidence interval? Very important that you know. We're estimating what? A true proportion or a true mean. Today it's all proportion. Tomorrow we're going to switch it and do means. Does that make sense? Guys good? Okay. Sure. All right, you guys want to see some cool calculator stuff? I'll show you cool calculator stuff. Cool calculator stuff. All right. I want you to go stat on your calculator. Let's see how you're going to stat. Now I want you to go over to tests. And you see all these tests over here that you have? You can actually do some of these in your calculator. So I want you to go to today's. Do you guys see the 1 proportion z interval? It's letter A in your calculator, 1 proportion Z interval. Once you press enter, your calculator will give you the interval, but will not do all the interpretation stuff. You got to know that. But it will give you the interval. What you do need is an X value, an N value, and a confidence level for it. So let's go back to example 2. So flip your paper back over to example 2. All right, what was your p hat value? 0.60, right? Am I going to put 0.60 there? No, you're not going to put 0.60 there. Why are you not putting 0.60 there? Because does it say to put p hat where x is? No, what does it say to do? Put x. So x is going to be n times p hat. AKA, it's going to be the number of successes. So when you did your condition check, you guys remember your condition check that you did? What did you get for NP hat for that example? You said 306, right? 306. So you're going to put 306 here. So X is the number of successes. What was your sample size? 510. And what was your confidence level? 90. Go ahead and calculate that once you change all those. I'm going to do it up here. So I have 306, right? 510. 510. Apparently it doesn't like the number 1. Did you guys get the same interval?
Yes.
Yeah. So this is a way that you can do the interval in your calculator and check yourself, right? I prefer that you do it by hand just to get used to what you're doing. And then later in the course, we're going to talk about more of what the calculator can do and how it's going to be more of a tool that we're going to use to do these inferential procedures. Does that make sense? Now, one of the things it cannot do is find sample size. So do you remember that example we just finished? Cannot do that. All right, cannot do that. Hey, that's the end of today's notes. Do you guys have questions, comments, concerns, anything? Okay. So, how long do these problems get? Well, they get a little spicy later. And later is not today. Maggie, that is the perfect thing. Later is not today. Let's focus on the present and stop worrying about the future. All right. Nothing else you want to talk about for 1 proportion Z interval? All right. So that's all my work on the PowerPoint, but I just did it. All right. Tomorrow what we're going to do is we're going to talk about this AP3 response. All right. And then we'll delve into 1 sample T intervals, and we'll talk about the difference between 1 proportion Z intervals and 1 sample T intervals. All right. What I'm going to do is now I'm going to pass out your homework, and I'm going to let you guys get a nice little 20-minute head start on that. Does that sound good? All right.